In string theory, the big idea is that everything, every particle, every force is just a tiny vibrating string. It's a beautiful concept, but it immediately raises a huge question, right? If that's true, what actually happens when these strings run into each other?
Well, that's what we're going to get into today. We are taking a deep dive into the world of string interactions. We're going to try to understand what physicists call higher order amplitudes, which is really just a fancy way of asking how the universe weaves itself together at the most fundamental level.
So here's the game plan. First, we'll look at the basics of string collisions. Then we'll check out the simplest possible interactions before, adding in all the wild quantum stuff. From there, we'll see how physicists can actually build these complex pictures. And we'll finish up with what might be the single biggest promise of this entire theory. Okay, to get our heads around this, we have to do a little mental reset. We've got to move away from the old picture of particles as tiny points crashing into each other and step into the world of strings. And as you'll see, the way they interact is fundamentally different and, well, way more elegant.
Now, you're going to hear the word amplitude a lot. All it is really is a number. It's the number that tells you the probability of something happening. So when physicists calculate an amplitude, they're just asking, what are the odds that these two strings will interact and give us this particular result? It's the absolute bedrock of how we predict things in physics.
And this is where it gets really interesting. On the left, you see the classic way we draw particle collisions. These sharp diagrams with jagged corners where point particles meet. But with strings, it's completely different. As they move and interact, they trace out these beautiful, smooth, continuous surfaces called world sheets. There are no sharp points, no single instant of collision, and that one simple difference, going from sharp points to smooth surfaces, is the key to pretty much everything that follows.
All right, so let's start with the basics. The first, simplest, most straightforward kind of collision you can imagine. Physicists call this a tree-level amplitude.
Think of this as the first draft approximation of reality. It's the simple, classical view of what happens when strings interact, before we add in all the quantum craziness. Visually, this interaction is represented by the simplest possible surface you can imagine. Basically, a sphere. Now, of course, before you can do any math, you have to follow the rules of physics. Unitarity is just, well, it's common sense, right? It just means the chances of all the possible outcomes have to add up to 100%. And BRST invariance? That's a much more complicated beast, but you can think of it as the theory's built-in nonsense detector. It's a super important check that makes sure the answers you get are actually physically meaningful. Without these two rules, none of this works.
But here's the thing. Our universe isn't simple and classical. It is quantum mechanical, right down to its bones. So now we've got to add that layer of quantum weirdness into our picture. And in string theory, that literally changes the shape of the interaction. See, at the quantum level, empty space isn't empty at all. It's this fizzing, bubbling soup of virtual particles that can pop into existence and vanish in an instant. In the old point particle picture, this creates loops in those diagrams. But in string theory, it does something way cooler. It punches holes in our smooth surface.
And this right here is the heart of the idea. A simple, classical interaction is a sphere. But the very first quantum correction, the most important one, is like adding a handle, turning that sphere into a donut, or what mathematicians call a torus. And as you account for more and more complicated quantum possibilities, you just keep adding more handles. The complexity of the physics gets encoded into the geometry of the surface. It's incredible.
I mean, just look at this thing. This isn't just an abstract shape. It's a picture of a really complex quantum event. Every single one of those handles represents another layer of quantum effects, another loop of virtual particles influencing the outcome. To figure out how likely this event is, you have to understand the geometry of this exact shape.
Okay, so you can see how these shapes could get insanely complicated, right? So how in the world do you calculate anything on a surface that has, 10 handles? Well, physicists came up with this really clever, almost crafty solution. They build them piece by piece. The whole concept is literally called sewing. You can take two simpler surfaces, say 2 donuts, and you can imagine cutting a little hole in each one. Then you just stretch and glue, or sew, the edges of those holes together. And boom, you've just built a more complex surface, one with 2 handles from 2 simpler ones.
So here's the really crucial insight. It turns out that even the most ridiculously complicated interaction can be broken down this way. It's like cosmic Legos. The fundamental building block is just a simple sphere with 3 little holes in it, representing 3 strings interacting.
By sewing these basic building blocks together in all the different possible ways, you can construct any interaction you can dream up.
This basically gives physicists a recipe. You start with your simple ingredients, you lay out the rules for how they can be connected, and then, to get the final answer for the total probability of an event, you just have to sum up every single possible way you could have stitched them all together. It turns a mind-bending problem into a step-by-step procedure.
And that brings us to what might be the biggest payoff of this entire approach. It's the hope that this geometric picture can solve a problem that has plagued physics for decades: the problem of infinities.
This quote from the source material really gets to the point. The number one goal, the holy grail, is to have a theory where your calculations don't just blow up and give you infinity as an answer. You want a theory that gives you sensible, finite numbers. So here's the problem in a nutshell. With point particles, those quantum loop calculations involve interactions at an infinitely small point, and that pointiness makes the math explode into infinity, which is just nonsense. Physicists have some very clever mathematical tricks for sweeping these infinities under the rug, but it always feels a bit like cheating. But string theory, it might solve this from the get-go. Because strings aren't points, they sort of smear out their interaction. And that little bit of smeariness is just enough to smooth out the math and avoid the infinities altogether. Now, to be fair, string theory isn't perfect. You can still get these troublesome answers, called divergences. But, and this is a huge but, they happen for a different reason. They don't come from a single point breaking down. Instead, they correspond to something you can actually picture, a geometric event, like one of those handles on our donut getting stretched infinitely thin until it pinches off. The problem becomes geometric, not pathological.
And at the end of the day, this is what gets so many physicists excited. When you try to combine our standard theories with gravity, they're just riddled with these nasty infinities. String theory, with its built-in geometric smoothness, offers this potential path, maybe the only one we have right now, to a complete theory of quantum gravity that is mathematically consistent and finite all the way down.
So let's just recap the journey we took. We traded point particles for little strings. When they collided, their interactions traced out smooth surfaces. We found that all the weirdness of quantum mechanics could be seen in the very shape of these surfaces, in the number of handles they have. And finally, we saw that even the most complex interaction can be built just by sewing together a few simple, fundamental pieces. It's this deep, profound, and totally unexpected link between the messy, chaotic world of quantum physics and the clean, elegant world of geometry that has kept physicists captivated by this idea for more than half a century.
Which leaves us with the ultimate question, doesn't it? Is this incredible mathematical elegance a sign that we finally found the true nature of reality? Or is string theory just the most beautiful, most powerful story we've managed to tell ourselves about the universe so far?